Welcome back to the second session of Plenary Speakers. It is my pleasure to introduce now the talk by Peter Kronheimer from Harvard and Tom Mrowka from MIT. Peter and Tom are specialists in a wide range of mathematical areas, including differential geometry, gauge theory, low-dimensional topology, and mathematical physics. They're co-authors of literally dozens of papers, and using Seiberg-Witten invariants, they settled long-standing conjectures, including the Tom conjecture and the property P conjecture for knots. In 2007, Peter and Tom won the Oswald Veblen Prize in Geometry of the American Mathematical Society for their contributions to both 3- and 4-dimensional topology through the development of deep analytical techniques and applications. Their book, Monopoles and Three-manifolds, won the 2011 Joseph Doob Prize of the American Mathematical Society. And the title of their talk today is Knots, Three-manifolds, and Instantons. So please welcome Peter Kronheimer and Tom Mrowka.
Well, it's a pleasure and honor to be here. We'd like to thank the organizing committee for the invitation and obviously the tremendous amount of work that they have invested in putting on this event. This talk has sort of 4 parts. Peter and I will switch on and off. Please don't applaud in between. Yeah, so let's begin. We're interested in the first part of the talk. I'm going to describe one of our theorems and try and give you a very concrete idea of what it means. So we're studying knots. A knot is an embedding of the circle in 3 space with no self-intersections. There's the trefoil. Here's the figure-8 knot. And the basic problem in knot theory is to understand if I have 2 such embeddings, when can I bend and stretch, etc., one into the other or not. Sometimes links appear in the story, so embedding of several circles. An important character in knot theory is the unknot, just the standard embedding that lives in a plane of the circle. And of course, there are many, many knots. If you organize knots according to the number of crossings in a projection, by the time you get to 16 crossings, there are nearly 1.4 million distinct knot types. So many that this poor knot 16N36441, this is its only moment of fame. The trefoil and figure-8 have a much more pleasant name. And because there's so many knots, there are tables of knots with knot invariants computed, so there are many interesting conjectures that come about in trying to see what kind of patterns appear. So the main question that we're going to focus on is, how do you recognize when a picture represents an unknotted circle or not? So is this a picture of the unknot? A basic tool in that study is the complement of the knot. And in studying the complement, it's natural to study its fundamental group. That's the group of homotopy classes of paths. Here I've indicated one such path that lives in the complement of the knot, starting at some base point, running around the knot, and then going back to a base point. Here's a different element of the fundamental group. Both of those curves are examples of meridional curves. They're curves that go around and loop around the knot once and then return back the way they came. Another important fact to keep in mind about the knot group is that it's abelianization independent of the knot. The abelianization is the group of integers, Z. And that leads to the first kind of recognition principle for when a given knot is unknotted. That comes from Dane's lemma, which was not quite proved in 1912 by Dane, and then finally given a rigorous proof in 1957 by Papakyriakopoulos. And it tells us that a knot is the unknot if and only if its fundamental group is Z, and if and only if its fundamental group is abelian. So for us, in trying to recognize knottedness, one way to test is to one way to certify that a given knot is knotted is to show that the knot group is not abelian. So, and we can recognize that by exhibiting a homomorphism from the knot group, a representation, with a non-abelian image. It's a theorem of Thurston's that actually knot groups are residually finite. So, in fact, we know that, therefore, that we could detect the non-abelianness by mapping our knot group into some orthogonal group, isometries of some Rn. It's an interesting question, then, will the same n work for all knots? Or if it does, is there a smallest n? So that's the content of the first theorem, which is that, in fact, if you have a non-trivial knot, then there's a homomorphism into SO3, isometries of R3, with non-abelian image. So that's one way of certifying knottedness, exhibit such a homomorphism. And as an example of this, so this is a sort of thing that's been studied for a long time amongst knot theorists. So the simplest example would be representations into dihedral group. So, symmetries of a Euclidean polygon allowing reflections. There are many knots that have no dihedral representations, but maybe not so many. Amongst the first, amongst knots with 12 or fewer crossings, only 17 don't admit dihedral representations. However, our theorem guarantees that all these knots and all others have representations into SO3. Now, I'm going to discuss a little bit, set up the story a little bit more for how this theorem is proved. So recall a meridian is a curve that starts, it's an element of the fundamental group, element of the knot group, represented by a curve that starts at a base point and then loops once around the knot and then returns to the base point. So we're going to look at special representations, representations that take all meridional curves to elements of order 2. Okay, so that maybe mild restriction. It turns out that that's good enough. A nice thing about this, these kinds of representations that map meridians to elements of order 2, well, we want to think about these kinds of representations. And a natural thing to do in studying, looking for the existence of one of these guys is to look at, try and understand the set of all such representations. So we're going to give it this name, R of K. That's the representation variety of the knot. And the question that we want to ask is, how can we get some kind of understanding of R of K, some kind of understanding that's uniform amongst all knots, and learn some properties about R of K. So, well, because we're looking at these special representations where meridians get mapped to elements of order 2, what we're doing then is to every meridional curve, we're associating an axis in R3, an axis through the origin. And we'll remember those axes by a point that they hit the 2-sphere on, the unit 2-sphere. So we're looking at, so these rows, these representations assign an axis to each meridian. Now, the axes will have a constraint. So here, the light blue curves in the picture there represent our knot. The two dark blue curves and the green curve, they represent some meridians for that knot. And our representation is meant to take the meridians and give us axes represented by the corresponding points on the two-sphere. And then the three meridians satisfy a relation in the fundamental group called a Vertinger relation. That relation implies that if it corresponds to a representation, that the corresponding axes, so the axis corresponding to the meridian B, if you do a 180-degree rotation around it, it has to switch the axes that the curves A and C go to. So that's the constraint. And as an illustration of this, let's take a look at the 5-7 torus knot. So the 5-7 torus knot is, so that's the 5-7 torus knot. And our game here is that to each meridional curve, we're supposed to associate a point on the two-sphere. So that gives rise to a very pretty pattern if it corresponds to one of these representations. So each, from this knot projection, I get a meridional curve by taking a path from my base point, approaching the plane of the projection, looping around one of the curves in that in the projection, and going back to the base point. So the light blue curves in the the light blue curves these curves correspond to meridians, and they get mapped to points on the two-sphere. And then there's the relation, as indicated here. So there's the purple dot on the left is a crossing, and on the right you see the corresponding relation played out on the two-sphere. So we get these very pretty patterns. So that's the kind of content of the theorem, that you get these pretty patterns on the two-sphere. And here, again, we're trying to understand this representation variety R of k. So if I look at the unknot, the representation variety is just the set of all possible axes through the origin, so a copy of real projective two-space that correspond to a single axis. And if I have a more complicated knot, well, I'll always have the representations corresponding to each meridional curve getting mapped to the same axis, a copy of real projective space, and then there might be some other stuff. And the other stuff corresponds to non-abelian representations, for sure. And then this is our, the refinement of the first theorem I mentioned, the non-emptiness theorem. If you have a non-trivial knot, then this other part corresponding to non-abelian representations of the representation variety is non-empty. And I will now turn over the floor to Peter.
Thank you, Tom. So what I'm going to do next is put this non-emptiness theorem in the context in which it belongs, try and explain the mathematics to which it's connected and with which it's proved. So the larger context is a context of three-dimensional manifolds. We've already seen the complement of the knot in three space. That's a three-dimensional manifold indeed. The three-dimensional manifolds we want to be thinking about now, unlike the complement of the knot, I want to think about compact manifolds without boundaries. So there's a closed three-dimensional manifolds. And also ask that these manifolds be oriented. So a three-manifold has a fundamental group, pi1, just as we considered the knot group earlier. And we can again look for representations of the fundamental group in a target group. And the target group, again, for us will be the three-dimensional rotation group SO3. So here it is. We look for representations rho from the fundamental group to SO3. So such representations rho in SO3, these were part of the work of Andreas Floer in developing the Instanton Floer homology that he constructed in 1986. And for several slides now, I want to be telling you a little bit about Instanton Floer homology, the background to it, and Floer's construction. So what we'll see in a nutshell is that we can think of what Floer did then as taking these representations, putting them into a package, and out of that package producing what Floer called the Instanton homology of the three-manifold M. So this is I of M in my slide. I of M, the Instanton homology, now usually called the Floer homology or Instanton Floer homology of the three-manifold. And it's a finitely generated abelian group, or if we prefer, it's a vector space over any field we choose. So I'm going to spend some time talking about how to construct the Instanton Floer homology. So the first step is to think more geometrically. The representations of the fundamental group, these arise more or less equivalently as flat connections in a principal bundle over the three-manifold. So given a connection, one has the holonomy around loops in the three-manifold. If the connection is a flat connection from the holonomy around loops, we obtain a homomorphism rho from the fundamental group of the three-manifold to the structure group, which in our case will be SO3. So this is a straightforward geometrical picture. There's a small point which I, in good faith, must introduce at this point, which is that we don't always want to work with SO3 as such. SO3 has a double cover, famously the unit quaternions, or the group SU2. SU2 has the topology of the three-sphere, and it's the universal cover of SO3. An SO3 bundle does not always lift to the double cover, an SU2 bundle. There's an obstruction to doing so. It's a characteristic class. So we won't be able to do the lift on the whole of the three-manifold, but we can do it on the complement of some locus, which we can choose in the three-manifold. That locus is here W. It's a codimension 2 locus because the obstruction is a two-dimensional class, and we can take it to be a simple closed curve. So that's what this next slide shows, a simple closed curve W inside the three-manifold M. On the complement of W, the SO3 bundle can in fact be trivialized. We can lift it to the double cover SU2. But there's an obstruction to extending over W itself. It's really only the homological content of W, the homology class that it carries in mod 2 homology, that is of importance to us and which we'll remember. So that's the obstruction to lifting the representation to the double cover. If we like, we can just consider those representations rho in bundles for which the obstruction class is a given class. We can choose the obstruction class in advance and just consider the corresponding homomorphisms belonging to that obstruction class. So we did some geometry, the holonomy, flat connections, a little bit of topology and obstruction theory in lifting to the double cover. But what I really want to talk about is the gauge theory and geometrical analysis, which we then apply in this situation. So this, again, is part of the work of Floer in developing the Instanton homology in particular. Representations rho are then flat connections, but we want to consider in gauge theory not just the flat connections in a bundle, but given a bundle, we want to consider the space of all connections in a given, in our case, SO3 bundle on the three-manifold. The space of all connections in a given bundle is an infinite dimensional space, infinite dimensional manifold, we can think. In this slide, it's necessarily presented as finite dimensional. That's this blue surface here. So the blue surface is for us the space of all connections in the principal bundle. Sitting inside the space of all connections are the distinguished connections which are flat. Drawn here as a single point labeled rho in the slide. So that's a flat connection sitting inside the space of all connections on the three-manifold. In 3 dimensions, there's a very special feature of this story, which is that the flat connections arise as critical points of a functional, and that functional is the Chern-Simons functional. It's a functional on the space of all connections. Here's a formula for the Chern-Simons functional. The flat connection, the potentially non-flat connection, the connection in the principal bundle, the argument of the Chern-Simons functional is here represented by A, which is to be a matrix-valued one form on the manifold. In the integrand there, for example, you see a cubic term, A wedge, A wedge, A. That'll be a matrix-valued 3 form, the cube of A. Its trace is an ordinary 3 form, which is integrated on the 3-manifold M. And there's a similar term there which involves the derivative of the matrix-valued 1 form A. Again, the integral of the trace of a matrix-valued 3 form. The critical points, the zeros of the gradient of the Chern-Simons function, are exactly the flat connections, portrayed here as like a saddle point for this functional. In this story, we need to consider, along with the critical points of the functional, the gradient flow lines of the functional. So I'm going to write down here formally the gradient flow equation. That's the time derivative of A. And on the right-hand side is the downward gradient of the Chern-Simons functional, written in terms of the representation by a matrix-valued form. This equation, there are 4 dimensions involved here, 3 on the manifold M, which is a 3-dimensional manifold, and now there's the 4th dimension of time. It's a very important feature of this equation in Floer's story that it's, although written here in sort of 3+1 form, it's really a fully invariant 4-dimensional differential equation, this equation. It's the anti-self-dual Yang-Mills equation in dimension 4. So this brings us to a large body of work in gauge theory. The Yang-Mills equation, self-dual Yang-Mills equation, this same equation, is the equation used by Simon Donaldson in the 1980s first in his study of the smooth topology of 4 manifolds. They were used there in his work as a tool. His work also built on the geometric analysis of essentially this nonlinear elliptic partial differential equation, and that geometric analysis was pioneered by Karen Uhlenbeck and Cliff Taubes shortly before. Returning to the constructions of Andreas Floer in this instanton homology, we're taking ideas now from Morse theory. We have a functional, we have critical points. We want to consider now abstractly a vector space constructed as the vector space whose basis elements are the generators. So there's one basis vector for each of the critical points. We can do this, if we like, over any field at the moment. The flow lines, the gradient lines between critical points, we can count when they're isolated. Between critical points of adjacent index, we can count the number of instanton flow lines. These are the solutions of this self-dual Yang-Mills equation. And this will define matrix entries, which defines a map from C to itself, a linear map. And this map is a differential. Its square is 0. And the vector space with this differential is now a complex. So with any complex, we can form the homology, the kernel of D divided by the image of D, and that's what we do here. And in this context, this homology group is called the Morse homology of the functional, in this case, the Morse homology of the Chern-Simons functional. So from the Morse theory picture, we've come up with a a vector space. I said we can use any field. For simplicity, we will use the smallest field, the two-element field Z mod 2. This is for simplicity at the moment, but actually later it's also of necessity. It needs to be characteristic 2 eventually. So this is the definition of instanton-Floer homology as Floer gave it. I've again written it as I of M. I've labeled I by a choice of W. I want to choose the obstruction class in advance and just consider the critical points belonging to that obstruction class. The Morse complex is constructed from the Chern-Simons functional. We take its homology, the Morse homology. That's a definition of the instanton homology for the three-manifold. This is much like my previous slide, reviewing the picture. We've taken the representations, we've packaged them, put them in gauge theory, applied Morse homology, and constructed this finite-dimensional vector space, the instanton homology of the three-manifold M, and it's a vector space over the field of 2 elements in our situation. This then for us is the main theorem I want to emphasize about the instanton homology of 3 manifolds. It's a non-vanishing theorem. It's saying something is non-zero. It's telling us that this vector space is not the 0 vector space. It's a vector space of positive dimension. The immediate corollary of the theorem, if the homology is non-zero, then the complex from which it's built must have been a non-trivial complex at least. There must have been some critical points. The set of critical points must have been non-empty. And that's this corollary, the non-emptiness theorem. It asserts the existence of SO3 representations with a specified obstruction class W. The theorem has a hypothesis. The very construction of the instanton homology technically requires such a hypothesis in most cases, and that's that the obstruction class be non-zero in actually a particularly strong sense, which is that the integer, there's a non-zero pairing with some integer class in the 3 manifold. In most cases, this simply just rules out the possibility that W is 0. So the non-vanishing theorem, we'll see analogs of it later in slightly different situations. I want to tell you a little bit about some of the tools the background is used to prove this non-vanishing theorem. The toolbox icon will reappear at various times to indicate results which depend similarly on the same toolbox. And I'm not going to tell you very much about any of the bullet points here. I've already mentioned that the work of Floer is involved, and it builds on the work of Simon Donaldson, who in turn built on the analytic work of Taubes and Uhlenbeck. That's a sort of geometric analysis input and applying geometric analysis to topology in dimensions 3 and 4, the sort of subject from the 1980s. There's also tools in geometric topology as well as geometric analysis here. In 3 dimensions, there's important work of Harkin in developing surface decompositions and normal surface theory. There's an elaboration of decomposition theory due to Dave Gabay, which is the theory of sutured manifolds. An important development, again, from the 1980s, in which he used to prove long-standing conjectures about surgery on knots. The architecture of the proof of the non-vanishing theorem very closely follows a proof of a result with a similar statement by Andreas Floer and Yi Ni. They proved a non-vanishing theorem not in instanton-Floer homology, but in Heegaard-Floer homology, which is somehow a cousin, indeed, of instanton-Floer homology. A lot of the structure of the proof is taken from the outline in their work. Finally, I want to mention some key calculations which were done by Vicente Munoz. The simplest three-manifold beyond perhaps the three-sphere that you might think of are product three-manifolds, a circle times a two-manifold. And the instanton flow homology can be defined in that context, and it has a rich structure. And what Munoz did was calculate the key features of the structure of the instanton homology for that particular type of three-manifold, the product of S1 and a three-manifold. So at this point, I want to hand back to Tom, who will return you to the world of knots eventually.
Thanks, Peter. OK, so with some understanding of the tools that are used, we're going to return to knots and go back to that non-emptiness theorem in that context and some applications of it. So again, we're studying representations of knots where the meridians get mapped to elements of order 2, and now, at least in very cartoonish form, I can tell you why that restriction is important for us, that we're looking at meridians get mapped to elements of order 2. You can think of those as providing a generalization, a kind of boundary condition for connections along the knot. And then once we have a boundary condition, we can apply the same Floer homology construction to get an invariant of knots, say, in the three-sphere. The invariant we call I sharp of k, so k is now the knot in the three-sphere, I sharp to kind of distinguish it from the invariant of three manifolds, which looks quite similar. Anyway, so so I sharp is a vector space associated to knots. Let's say vector space over Z2 for simplicity. And as Peter mentioned, although in the beginning of the talk we're looking at SO3 representations, it turns out to be more convenient to look at SU2 representations. The representation variety R of k, once you go to SU2 representations, has a double cover itself. R tilde of k, and so for example, if I look at the unknot, then I think of replacing the real projective space that was the representation variety by a two-sphere. So now repeating what we said before, but in the context of SU2 representations, what we're trying to see, our theorem said that there were these, if you have a non-trivial knot, there are non-abelian representations. So the representation variety R tilde for a non-trivial knot should consist of a two-sphere and some non-abelian representations. That part's not empty if the non-abelian part's not empty if the knot is non-trivial. Now, of course, the homology of the two-sphere is a rank 2 vector space with Z2 coefficients, if we're working with Z2 coefficients. And it turns out that that picture, after a lot of work, it carries over to the instanton Floer homology of knots, I sharp of k. So for the unknot, the instanton Floer homology is a rank 2 vector space. And the way that the instanton Floer homology comes into the story is that we'd like to see that for a non-trivial knot, I sharp of k is, well, there's a rank 2 piece that comes from the two-sphere there, and hopefully there's some other stuff. So the rank of the instanton Floer homology is bigger than 2. And that's true. I sharp of k provides a way of certifying knottedness. This R from the previous slide is positive. For a non-trivial knot, I sharp of k has the dimension bigger than 2. And it's the unknot if and only if the dimension of I sharp is exactly 2. So this theorem uses the previous toolbox, and as far as we know, there's no other way to guarantee the existence of the representations other than combining all this geometric analysis and geometric topology into a big machine to try and attack these problems. Now, as you can imagine, from the definition, it's extremely hard to actually compute anything. In order to, if you wanted to compute from the definition I sharp of k, well, you'd have to first prove, you have to find all the representations of the fundamental group of the knot. Then, even worse, you'd have to solve this nonlinear partial differential equation, understand its space of solutions, and, you know, good luck. But it is a homology theory. It has properties that allow its computation without actually knowing the nitty-gritty of representations or instantons. And in fact, the I sharp of k is related to another popular important invariant of knots, the Havanov homology. So the Havanov homology has the same kind of shape. To each knot in the three-sphere, it assigns a vector space, or let's again think of it as a vector space over Z2 for the moment. One of the interesting aspects of Havanov homology is that it's related to the Jones polynomial. So you can obtain the Jones polynomial from knowing the dimensions of Havanov homology as a bigrading, and from knowing the dimensions of the pieces, you can recover the Jones polynomial. The wonderful thing from our point of view is that Havanov homology is computable. It's entirely algorithmic construction. You start off with a knot diagram. Havanov tells you how to construct a complex, compute the homology of that complex, and you can write computer programs. So the left part of the slide shows the result of such computer computations. And for example, for this knot that we've been carrying along throughout the talk, that's its Havanov homology. With z coefficients, actually. And Havanov homology has its roots in a very different part of mathematics, in representation theory, quantum algebra. So Havanov homology, almost by definition, satisfies the following so-called Skane property. So I imagine I have three different knots, which outside the three boxes are identical, but inside the three boxes they differ as the picture indicates. So, you know, you do the Macarena, and then you get the three knots. So the Skane property of Havanov homology is that these three knots, their Havanov homologies are related by a long exact sequence. So you know, standard bread and butter of algebraic topology appears in this context here. Well, it turns out that I sharp of k satisfies exactly the same Skane exact sequence. So same situation, and I sharp fits into a long exact sequence. Now you can kind of iterate this, and when you do that, you discover that there's a spectral sequence that comes out from this shared Skane relation. And that provides a deeper connection between the two theories. There's a spectral sequence that starts off with Havanov homology, and then further differentials give rise eventually, it abuts to I sharp of k. In particular, the dimension of the Havanov homology is at least as large as the dimension of the instanton Floer homology. Now, this result, it parallels, again, Peter mentioned Heegaard-Floer homology, it parallels some results of Ashvath and Szabo in Heegaard-Floer homology, where a sort of different spectral sequence appears, but motivated this work. So a corollary of the unknot detection result for instanton from Floer homology tells us that actually Havanov homology also detects the unknot. So If K is non-trivial, then with Z2 coefficients, the rank of the Havanov homology must be bigger than 2 because it must be bigger than or equal to the instanton homology. And again, part of the interest in this theorem is that Havanov homology has its roots in representation theory, quantum algebra, that sort of thing. But in order to prove this, so far, you need the toolbox. You need geometric analysis and geometric topology in order to be able to see this result. By the way, it remains an open question as to whether or not the Jones polynomial itself detects the unknot. And it would be quite interesting to see if that's true, what tools you'd need in order to prove it. So the Havanov homology is an unknot detector. And now you. Yes. Back to Peter.
Thank you, Tom.
Yeah.
So for the remaining segment of this talk, I want to broaden the context from knots a little bit. In the slide now we see spatial graphs. So graph here in the sense of graph theory, more or less, which is to say vertices joined by edges. But the vertices and the edges are embedded in 3 space. Not a very interesting embedding in the picture there, but that's the edges of a tetrahedron thought of as a spatial graph. So the difference from knots to spatial graphs is the introduction of vertices. When we talk about a spatial graph as topologists, we don't actually require that there be any vertices. So a knot is actually, for us, a special case of a spatial graph. Here, there's some other examples, slightly more interesting spatial graphs. The tetrahedron again. The next one is the Hopf-link again, 2 circles linked, but with the addition of an edge joining the 2 circles, introducing 2 vertices. The third one there, it has this sort of 5-fold symmetry, is abstractly as the underlying graph, a famous object, the Peterson graph, to which I will return. It has 10 vertices. All the graphs on this slide, and all the graphs you want to consider, are trivalent graphs. That is to say, at every vertex, exactly 3 edges meet. And those are the only sorts of graphs we want to consider. I want to draw attention to one other feature. This last graph here on the far right has what we'll call a bridge. So in our specific context of spatial graphs, a bridge means an edge for us, which perhaps after isotopping, moving the graph around in 3 space, the edge has the property that it's hit by a plane. There's a plane in 3 space which intersects the graph at one point of that edge, no other points of the graph, and separates the graph into 2 pieces. So this graph can be cut in 2 by a plane meeting the graph in a single point in that edge. So that's a bridge. We're not really interested in graphs with bridges very much. More typical of the ones we're interested in are these other 3. These are bridgeless spatial graphs. So trivalent, bridgeless spatial graphs are our object of study. The construction of instanton Floer homology for, well, first 3 manifolds and then for knots extends to spatial graphs. So I'm writing G for the spatial graph now instead of K for the knot. Just like the knot, it has a complement in 3 space, R3 minus G with a fundamental group. And again, we can look for homomorphisms from the fundamental group to the group of 3-dimensional rotations, SO3. Just as in the case of knots, we can and we will impose a restriction on these. We want to consider those homomorphisms, rho, which map meridional elements to elements of order 2 in SO3, a rotation about an axis in 3 space. A meridian is just as it is in the case of a knot. It's an element of the fundamental group represented by a small loop linking one of the edges exactly once and then joined to the base point, which is used in defining the fundamental group. So considering the space of all such representations for a given graph G, we have what we'll call the representation variety for the graph. And again, we'll write that as curly R of G. So far, this is just as we said for knots, and we're going to continue along the same set of rails and follow Floer's construction of his instanton-Floer homology group. So just as in the case of knots, we want to reinterpret these representations as flat connections. It's an elementary geometric step. We can then regard the flat connections as critical points of a Chern-Simons functional on a suitably constructed space of all connections in a suitably constructed Chern-Simons functional. And then again, we have this Morse theory package of Floer, which allows us to take the representations and the Morse theory and come up with a Morse homology group, a complex, the homology of that complex, which again, we'll call that the instanton-Floer homology, now not of a knot, but of a spatial graph G. There's a small change I want to make from the knot and three-manifold story that we talked about before. We chose to pass from SO3, the three-dimensional rotation group, to its double cover, the three-sphere, the group SU2. We're free to do the same thing in the context of spatial graphs, but for this talk, I don't want to do that. I want to stay with SO3, and that's the reason that I've called the group J sharp of G rather than I. The difference between I and J is just to remind us of that little change we've made. So this is a three-dimensional rotation group SO3, and SO3 instanton-Floer homology group for spatial graphs. Once again, it's a vector space over now the field of two elements, Z mod 2, and it's finite dimensional. Once again, and using the same toolbox of geometric analysis and classical geometrical topology in dimension 3 surface decompositions, we prove a non-vanishing theorem for the instanton-Floer homology now of spatial graphs. For a spatial graph G with one hypothesis that there's no bridge, the instanton-Floer homology is a non-zero vector space. Finite dimensional vector space of positive dimension. Once again, a corollary is the existence of elements of the representation variety. The representation variety must be non-empty now. The corollary stated here, representations exist from the fundamental group SO3, satisfying this constraint on the meridians. In the case of knots, the theorem of interest was that the non-abelian part was non-empty. A priori, there may be some abelian guys here or not. It's not clear. I'll return to that in a moment. But the statement is just the non-emptiness of the representation variety itself in toto, and you can amuse yourself by taking an example such as the Peterson graph or the one skeleton of a dodecahedron, and just going looking for the representations, and they're there to be found in those rather small examples. I want to ask the question now: what is this J sharp of G? What's it measuring, and what's it doing for us? We don't expect for this rather general question an answer other than it is what it is. But in cases that I want to describe, there's a connection I want to highlight. And it's a connection between this instanton homology group, at least, and a classical concept, which is Tait colorings of the underlying graph. So this slide is supposed to tell you what a Tait coloring is. It's illustrated there by example. The graph is the one skeleton of a dodecahedron. What is a Tait coloring then? It's a coloring of the edges using 3 colors: green, blue, red. And it's an edge coloring with the constraint that at each vertex, the 3 colors are different. We have to use all 3 colors at each vertex where 3 edges meet. So an example of a solution to that problem for the dodecahedron is there. That's an example of a Tait coloring of a trivalent graph. To be able to refer to it briefly, I want to just introduce a notation. I want to write Tait of G for the number of Tait colorings of a given graph G. So here's some pictures and examples. The one skeleton of the tetrahedron, the edges of the tetrahedron. There's a Tait coloring. There's essentially only one way to color the tetrahedron with 3 colors, but you can permute the 3 colors, red, green, blue, 6 permutations of 3 letters. So we regard those as different colorings, and we therefore write number of Tait colorings is 6 for the tetrahedron. For the dodecahedron, the number of Tait colorings is 60. Here's the Peterson graph again. It's the simplest example of what is sometimes called a snark in graph theory. The underlying graph here has no Tait colorings. It's in fact, the smallest bridgeless graph with no Tait colorings. Tait colorings have a little connection to representations of the fundamental group. I mentioned abelian representations a moment ago. In this context of graphs, there still exist abelian representations we want to look at, but not cyclic. These are representations whose image is the Klein 4 group in SO3. That's the abelian group consisting of the identity element and the 3 rotations about 3 orthogonal axes, 180-degree rotations about 3 orthogonal axes in 3 space. If we wish to map the fundamental group to the Klein 4 group and map meridians to elements of order 2 in the Klein 4 group, there are 3 elements of order 2 to choose from in the Klein 4 group for each edge, for each meridian. So we're essentially 3 coloring the edges, and it's easy actually to see this is exactly a 1-to-1 correspondence. Homomorphisms from the fundamental group to the Klein 4 group, those are exactly Tait colorings of the underlying graph G. So elementary 1-to-1 correspondence. But there's a deeper connection when you look at instanton homology. This term is stated for planar graphs. So for me, a graph is planar. Being a spatial graph, for it to be planar, I want it to actually lie as a spatial graph in a 2-plane in R3. This is different from the abstract question of whether a graph can be embedded in the plane or not. It's planar for me if it's actually in the plane. And here's the theorem. It's an inequality between the dimension of the instanton homology group and the number of Tait colorings. The hypothesis of being planar, conjecturally, that's not needed. Wouldn't say this is a theorem in progress, but it seems reasonable to us to try and prove that you can remove that hypothesis. I'm happy to conjecture this actually holds for all spatial graphs G. What I'm more interested in, though, is a continuation of this conjecture. What should really be special about planar graphs, we hope, is not this inequality, but that for planar graphs, equality should hold. So I'll put that there as a conjecture. I'll highlight it again here on the next slide. I'm restating the same thing. Equality should hold for planar graphs. The dimension of the instanton homology should equal the number of Tait colorings. This conjecture is of interest to us because it connects to the 4-color theorem, and I want to spend the last few slides explaining why this is so. Recall that we stated a non-vanishing theorem that's proved. The non-vanishing theorem said that the dimension of the instanton homology, J sharp, is positive for bridgeless graphs, which is the ones really we're interested in. Well, if the instanton homology has the same dimension as the number of Tait colorings, then of course from the conjecture it would follow that the number of Tait colorings is also positive for bridgeless planar graphs. So that last box is a corollary of the conjecture together with the non-vanishing theorem. So this last conclusion here, number of Tait colorings is positive, is essentially the four-color theorem, as I want to explain. So Tait, Peter Guthrie Tait, thought about many things. One of the things he thought about was the four-color theorem, and that's why Tait colorings exist. He made some observations. First of all, he thought about the four-color theorem, the question of whether we can color the regions of a planar graph with four colors. He realized that it's enough to consider trivalent graphs. So in fact, bridgeless trivalent graphs in the plane are what we should be thinking about. And he made the elementary observation that Tait coloring the edges is equivalent to four coloring the regions. And this, he didn't use colors, he used symbols, but this table here, essentially in his papers, and tells you how to do this, is a lookup table. Given the colors of neighboring regions, how am I going to color the edge between them and vice versa? And you might recognize this is the multiplication table for the client foregroup. So because of this, the four-color theorem is entirely equivalent to the statement that you can Tait color the edges of a bridgeless trivalent planar graph. So to recap this little corner, we have a conjecture about the equality between the dimension of J-sharp and the number of Tait colorings. A conjecture, I'd say, which I'm not going to bet my house on at all. I think it's a natural conjecture to make. It's similar to other questions where we know the answer is yes, but maybe this is a question where the answer is no. But we're motivated to make it because in combination with the non-vanishing theorem, it implies that every bridgeless planar trivalent graph has a Tait coloring. And then via Tait's work from the 19th century, this is equivalent to saying that the regions of planar graphs can be four-colored. This, of course, is the four-color theorem. It's proved by Appel and Harkin in the 1970s and reworked several times since then. Back in the 70s, this was one of the first serious proofs that involved computer assistance. And of the reruns of the proof and the reworking since, it's always a theorem which has required computer assistance for its verification. So this then is a motivating project for us. We have a conjecture about the instanton homology and its dimension. We have existing theorems on non-vanishing of the instanton homology. And if we combine the conjecture with the existing theorems, we obtain a proof, perhaps, of the four-color theorem, and one which might be, in some sense, a visible proof, a proof without computer assistance. So that's the motivating project for us at the moment, and it just remains for Tom and me to thank you both for your attention and to thank the organizers once again for all their work. Thank you.
Well, this was really a beautiful talk, and we're very grateful to the authors for having explained these connections between knots, three manifolds, spatial graphs, and with this last mention to the four-color theorem. As you probably know by now, there will be no questions, but the authors told me that they would be very happy to answer your questions in case you want to come up and say hi during the break. So let's thank the speakers once again.